So let's start this AGEA seminar. The first speaker of this afternoon is Qifeng Li from Shandong University. So he will talk about the deformation rigidity of wonderful group communication. Okay, welcome.
Thank you for the invitation and thank you for the introduction. As introduced, the title of my talk is Deformation Rigidity of Wonderful Group Communications. Today, this is the sketch what I will talk. Firstly, I will introduce the problem and then study the most important concepts VMRT is related with this talk, and then give some introduction on the general deformation problem and about spherical information, and finally to return to the proof. This happens to be the joint work with Professor Bohafu. We work over the field of complex numbers. Firstly, let's fix some notation and concepts will be used throughout the talk. Let G be a simple algebra group or semi-simple. Firstly, it's of rank R and adjoint type. Let's explain adjoint type. Here, if we consider the special linear group SL R plus 1, then when we quotient the center, we get PGL R plus 1. This is the corresponding adjoint type group of type A, and it's of rank R. Here, G is a group, but it's itself is also a homogeneous space. Here, here we consider the two-side multiplication. By AB is an element in G cross G. It acts on a point X on this manifold G. And the action is AXB inverse. Totally, this is the left action. Here, by a classical theorem and famous theorem of de Courcey and Procesi, there is a unique G cross G equivalent computation of this homogeneous space we denote by G bar, such that G bar is normal and compact. And G bar is our Picard number 1, and there is a unique closed orbit. Such kind of computification is unique. Moreover, this computification also satisfies some very nice property. For example, G bar is a smooth funnel variety, and the boundary or the complementary of the open part is a union of smooth divisors with normal crossing, and the number of these irreducible divisors is exactly R, the rank, and also the Picard number. Here, by take a subset I of this set from 1 to R, we can denote by the intersection of Xj. This is Xi. This Xi is just an orbit closure, or it contains itself contains a unique open orbit. So, I'll say the main orbit. This gives a one-to-one correspondence between the subset of this set and the orbits on this computification G bar. The closed orbit is just the product of four flag variety. And each orbit closure is also admits some nice property. It's smooth projective, and it's a fibration over a homogeneous space, and fiber is itself another wonderful group computification. So it also admits some universal property. Let M to be some normal complete variety, and suppose there is a left G cross G action with open orbit G and unique closed orbit. This is just looks like this property. here, then we can extend. We can get a birational morphism with the EC equivalent with connected fibers, and the open orbit is the identity. So in this sense, this G bar has some nice property and universal property. Now we continue to construct this compactification. Previously, is some abstract existence, but we can construct it explicitly. Here, we firstly recall that G is has no center, it has a trivial center, but now we consider its universal cover. It's a simply connected algebra group. We use GSC to denote this cover. Then let V lambda to be some irreducible representation of this group, and the corresponding highest weight to be lambda. As this is representation, so we have a homomorphism of groups from GSC to GLV lambda. Then we quotient center get a homomorphism from G to PGLV lambda. This is the open subset of P into V lambda. Let X lambda to be the image closure of this G. This X lambda has a unique closed orbit. It's a self-product of a flag manifold. So when this lambda is regular, then this X lambda is just our G bar. In particular, this X lambda is independent of the choice or lambda as long as it's regular. Now we also give a more complete, more explicit construction of type A case. Let's construct the compactification of AR. Recall that AR represents the group PGL R+1 as we explained. This is an open subset of this P into R+1. This is just the projectivization of matrix space. As matrix, for matrix, we have rank, a concept as rank is well known. So we then we consider rank, the rank of this matrix. Let ZK to be the set of matrix with the rank at most k. This gives a chain from Z1, Zk, Zr to this total projective space. Note that this Z1 is just self-product of projective space, and Zr is just the set of singular matrices, so it's a prime divisor. Then how to get this wonderful compactification? We just take the successive blow up from the smallest Z1, then blow up the straight transform of Z2, continue. Finally, we blow up the straight transform of Zr-1. Then now we get the wonderful compactification. In particular, if the rank R is 1, then we blow up nothing. In this now, so in particular, we know that the wonderful compactification of PGL2 is just the projective space P3.
So question. So before so what's the fiber of this block? Is there still wonderful communication?
No, because this is smooth blow up. As far as in my impression, each step is smooth blow up, so it's projective space.
Yeah, but I mean, if you fix 1 point in Z1 in the first locus, and then you consider the fiber after these blobs. It looks like to be a successful. Yeah, it looks like to be a smaller wonderful communication with smaller groups. No.
I'm not sure. Maybe not. I don't know. I really don't know.
Okay.
It's a little involved, so I need some paper and pen to check it. Maybe I will think it later. Sorry. Let's continue to the later part. Now let's introduce the problem. The problem is about deformation rigidity. Let's given a connected final manifold X, we see it's rigid and final deformation if for any smooth family or connected final manifolds, if one particular fiber is this X, then all other fibers are also this X, by holomorphic to this X. In this sense, we see X is rigid and final deformation. Or in other words, if we give a connected give a family of final manifolds, if it contains one fiber is this X, then we can't contain other fiber. This means the rigid. So our theorem with my theorem with the first full is this, the variety G bar, this compactification. This variety is rigid and final deformation. Recall that we have explained that this G bar is a connected final manifold, but its Picard number is very high. To show these results, we have there are two main steps. The first step is due to Bian and Brillon. It's about infinitesimal rigidity. By their results, the tangent bond has vanishing first order cohomology. Then, by Kodaira-Spencer theory, this G bar is infinitesimally rigid. Then now the problem tends to be a specialization problem. In other words, we have a family. In the previous family, X, we can suppose general fiber is G bar, or even every non-zero fiber T is G bar. We need to show the central fiber X0 is also G bar. We have another remark to reduce the problem. Recall that G is semi-simple because it's centerless, so it can be written as product of simple factors G1 to Gm. Each Gi has a wonderful compactification. Their product is exactly the wonderful compactification of G. So by a result of myself, the product result structure is preserved and final deformation. So we can see that we can reduce the problem of this specialization to be this G is also a simple algebra group. So in the final part, when we prove this result, we will only consider the specialization with the problem with G to be simple. In our study of this problem, the most important concept or theory is about VMRT. So let's introduce some basic information about VMRT. Let X to be a smooth projective unirod variety. K to be a irreducible component of family of rational curves. If for a general point on this X, this point is small x, so this Kx is non-empty and projective, then we see that K is a minimal rational component. The element of this K are called the minimal rational curves. Here, note that since this point X is general, so this Kx is smooth. Now let's continue to keep X key and the small point, the general point to be as above. So we know that general elements in Kx are indeed smooth at this point, X, and then we can get a rational map. It sends the minimal rational curve to its projective the tangent direction or at this point. So this is a rational map. The image closure is denoted by Cx is called the VMRT, or say the variety of minimal rational tangents. By a result of Huang and Mock and another result of Kipkers, we know that this rational map is indeed a birational finite morphism from Kx to Cx. Since Kx is smooth, so this is indeed the normalization map. Let's consider some example about the VMRT. The most basic one is about the projective space. Then the minimal, it contains a unique minimal rational component. It's just the family of lines on Pn. The VMRT is just the total tangent space. Of course, we need to projectivize. Then the next case is about the smooth hypersurface. If the degree is small, then the family K, the minimal component is also the lines on this variety. And the VMRT is the complete intersection of some other hypersurfaces is associated with the equation of this X. Let's consider the other, the wonderful group compactification case. Recall that we have constructed the compactification of AR to be some successive blow-up of this space, and the first blow-up center is Z1 is self-product of PR. If we take a general point in this AR bar and P to be the image point, then we know that this Kx minimal component passing through this point, general point, is just a straight transform of lines from P and connect P and with ZY. And the VMRT is just, roughly speaking, is this ZY, but we need to a one-dimensional projection. Center is this point P. On this G bar, we have a lot of rational curves. For example, given any root alpha, we can has a unipotent group, one-dimensional unipotent group U alpha, and one-dimensional multiplication C star. So when we take the compactification of this these two groups, we get smooth projective rational groups. The minimal rational curve on J bar is just among these two classes. More explicitly, it's a result of Bohemian and Fu. There is a unique minimal rational component of K on J bar. If you take theta to be the highest root of this group J, then this U theta bar is a minimal rational curve. And by taking the group action on the G cross G group action on this curve, we get a lot of minimal rational curves. Usually it's the other one. Let's say at the base point E of J, this tangent map from KE to CE is indeed an isomorphism. If we return, in particular, this CE is small. If we consider the case J is not AR, then this VMRT is just, recall that at E, the tangent space is, or J is the Lie algebra. So this J is a irreducible representation of J. So it has a unique closed orbit, G quotient P theta. This is just the VMRT. If J is of AR, we just explained the Wehrmacht is roughly, this is self-product of this PR. Indeed, it contains this orbit or closed orbit as a hypersurface. Note that at other points, we can use group action to get the Wehrmacht is the general point of this G bar. We can use group action to get the identity of Wehrmacht. So this is the Wehrmacht at the general point. Now we introduce we explain the deformation rigidity problem usually. There's a framework introduced, let's say, from the series works of Huang and Mock about deformation rigidity. Firstly, according to their series works, we know that rational homogeneous space of Picard number 1 are rigid and smooth Keller deformation. Here there is a 7-dimensional case as an exception. It has some special degeneration. The framework of this kind of rigidity problem is like this. Let's consider their case. Firstly, we consider the specialization problem. The general fiber is this G cushion P alpha, rational homogeneous space of Picard number 1. We know that the minimal rational component of general fiber deforms to a minimal rational component of the central fiber. And this deformation, the Wehrmacht is also preserved by some work. We can find that the Wehrmacht is the same, or in other words, the Wehrmacht at the general point of x0 is the same as the Wehrmacht of G cosine P alpha at the base point or any point. The final step is that it's a recognition problem. Is recognized the manifold by the Wehrmacht. By works of several people is firstly is the work of Mock, then joint work of Hong and Huang and Huang and myself, and then Huang, myself, and Timoshev. Several works. We know that the rational homogeneous space of Picard number 1 could be recognized by the Wehrmacht, or in other words, if explained explicitly, let X to be a final manifold of Picard number 1. It has same dimension of this homogeneous space. If at the general point is Wehrmacht is the same of the Wehrmacht of this homogeneous space, then this X is bi-holomorphic to this homogeneous space. Here I should say that this recognition sketch, or say this framework, is a little different with their original sketch, how this rigidity problem is solved, but the spirit is, or their work is the same. Indeed, this recognition problem comes from their work. This framework seems to work well for many Picard number 1 cases, but for general high Picard number case, this recognition problem may be failed. On the other hand, for higher Picard number case, we have birational geometry as an advantage. We have a lot of results from birational geometry. They can help us.
One question before you, for this theorem, so you assume for X general. So if you assume it exists just one point, suppose X has one point with the same Wehrmacht, then it's okay or no?
But let's say the one basic question is that whether this Wehrmacht has the expected dimension. If the dimension is not the expected dimension, it can't help us.
Okay.
So I'm not sure this could be automatically fulfilled if we suppose some special VMRT, very special VMRT. I'll say the VMRT at a very special point is some less smooth and very nice.
But the VMRT of Chimo P, most of them are rigid.
Yeah, yes, but this kind of thing for let's say this is, I guess this may be possible, but the first difficult part is to solve this, whether this point, even the VMRT at this point has different fiber with others to exclude this possibility. For general case or for the most case of rational homogeneous space, we are not sure, but we know that especially like something like if the VMRT is linear, is projective space, so linear subspace.
Maybe it's okay.
Okay. Let me continue. This is a hard question indeed.
Can I ask a question about the second condition?
Okay.
So do you assume there is one general point, or do you assume that for all general points, the VMRT is the same as the rational homogeneous space?
We assume for this works at open subset, but this is, let's say, there's not a big difference, as explained by Professor Foot that now he mentioned. This VMRT, they are locally rigid. This VMRT, they have some kind of local rigidity. If just assume one general point, so use the local rigidity, we can get the nearby fibers. At least we are sure almost everyone has this automatically satisfy this property, because most of them are indeed homogeneous. So some the special case also has such kind of property, but need some argument. Could this answer your question?
Yes, thank you.
Let me continue. Now let's explain, introduce some rigidity property for usual final deformations. This comes from a series works, several works. Firstly, from Professor Xiu, then Professor Wisniewski and Hicken, and indeed also there are also some other works related with this work. Firstly, let's consider some nice case. Let's peg to be a holomorphic family of Fano manifolds. Then we know that this numerical space N1 is invariant under this deformation, and it also coincides with the second cohomology. And the Picard group is also invariant. Then we regard this as identity, and this identity, the Neff cone of divisors, mobile cones of divisors, pseudo effect cone of divisors are invariant. Also, the Murray cones are invariant. If we consider some line bundle on this family, consider the restriction map. This map is surjective, and it has a very important. It has a important corollary is that this space, the dimension of global sections is invariant along this family. This result, let me give some remarks on these results. Firstly, although I state on the analytic setting, this work results also works in algebraic settings, and most of these results works for family of Fano variety with the terminal Q factorial singularity. But we only need this nice case, so I only state this case. I should remark this because, for example, this invariance of Picard group for this singular case is also very non-trivial result. Finally, let's not final. Now let's return to the spherical information, or see the spherical theory. Our variety is a spherical variety, and it's important in our work, and this is also a nice theory. So I would like to introduce to you. Let's firstly give some general definition. Let L to be some connected reductive group, B to be a fixed Borel subgroup. Then a normal variety with the L action is called spherical if under this action there's an open B orbit. Here, in this case, for another Borel group B prime, we can also find the open B orbit, B prime orbit. So this B is not so, choice of B is not so important. Also, in this case, we can find an open L orbit. So in particular, X must be quasi-homogeneous. I recall that our homogeneous space G has a G cross G action, as we explained in the beginning. Then we can use the Burkhardt decomposition to study this G and G bar. Let B to be a Borel subgroup, B inverse to be the conjugate. For example, if G is PGR R plus 1 comes from special linear subgroup, so B could be recognized the upper triangular matrix. B inverse could be the lower triangular matrix. So this is just a multiplication of this matrix. We know that this is inclusion is open. This is also open. So by this definition, G and G bar are spherical variety. And use the we also return to the bracket decomposition. This is the open orbit. We also has some good-dimensional orbit. Is like for each root alpha I, we have a reflection sigma I. Then B sigma I, B inverse is a codimension orbit of this G. Take the closure on this G, then this prime divisor is called a color of this variety, or this spherical variety. Note that this boundary G delete BB inverse is just a union of this R colors. This R is just the rank of G. There's a one-to-one correspondence between the spherical variety with the open orbit G and the colored fans. This kind of theory is an analog of, if you know toric variety, then maybe you can remember each toric variety corresponds to a unique phi in this lattice space. Width space, sorry, it's not width space. This is the analog, the theory of spherical variety is analog of this the theory of toric variety. This lambda G is just the width lattice. Now, this kind of theory has a very on the geometric information of this or spherical varieties could be explained by this combinatoric information. For example, the Picard group of G bar is identified with this width lattice, and this, if we identify them with the equality, then this color Di corresponds to the i's fundamental weight omega I. Recall we have the boundary, I mean G bar delete G. This boundary is a union of it's a smooth crossing with a union of R divisors. This boundary divisor Xj corresponds to the root JS root alpha J. Then the anti-canonical divisor is just has a explicit formula. We also know the under this identification, we also know the Neff-Cohen divisors is just a simple sum, simply Shao-Cohen, and it coincides with the positive wire chamber. The Cohen pseudo-effective divisor is also simply so. It corresponds to the, roughly speaking, it corresponds to positive roots. In particular, because this is a finite sum, in particular, we know that all pseudo-effective divisors are effective. The Murray-Cohen also has some correspondence with the positive, let's say, co-roots. We also has a criterion about the line bundle to be Neff. Okay, yes, we have a criterion, but I did not write here. I just give some remark about Neff-like models, because each Neff-like models are globally generated. So let me skip this part. Is maybe you can feel involved. Here I explained the just now I said there's a one-to-one correspondence between the spherical variety with the colored fan. Here I give the explanation about the colored fan, but maybe you can feel involved. So let's just remark on the last part. Recall that our G bar is a compactification of the group G. On the G, we have a maximum torus T. If we consider closure of this T is just a toric variety, it's a funny thing like this. It's phi is a toric variety. It's phi is well known, and it's just consists of wire chamber and the faces. So by this, I just want to say that all the information of this G bar or even the T bar could be recognized by the representation theory. Finally, let's turn to explain briefly how, not so brief. Let me explain how to prove our first result, our main result, and introduce you something about what I explained just now. Recall that we need to consider a specialization problem. It's a family X over direct. So every non-zero fiber at non-zero point T is G bar, and this G is a simple algebra group or adjoint type. Firstly, we know that the family of minimal curves on general fiber deforms to a family of minimal curves on the central fiber. Here, I need to say that the final condition is important, because here, because this is very high, it's a high Picard number case, so this is not trivial. And moreover, we also know that VMRT is preserved. For general case, we can, because we know the VMRT of wonderful group communication, most cases is a rational homogeneous space. So we can use the deformation rigidity of rational homogeneous space of Picard number 1. And this is although not enough to know the inverse of VMRT, but it's the key point. Then we need to apply the results about the we explained the result of Shaw and Hicken with Wisniewski about the rigidity property and the final deformations. So there are also some special cases we need to study, but we also need we use the deformation rigidity property and the final deformation to get this. Roughly speaking, it's just a compensation of the knowing previous results about differentiality of rational homogeneous space and the special property of final deformation rigidity to get this WMRT invariance. So according to the original plan, it's the recognition problem, but we know it's failed. So how do we overcome the difficulty? Now let's recall a property from Huang and Mok and Fu and Mok. Huang, let X to be a smooth projective uniform variety. Suppose the WMRT is nice, let's say. Then the dimension of automorphism of this variety could be bound by this automorphism the algebra of this CX. It has a explicit formula, and when the equality holds, we know this WMRT has some flat structure. Return to our case. Suppose G is not type C. Then we can apply the previous formula to know that the dimension of automorphism group of central fiber is 2G plus 1. Here G is the dimension of this group G. Note that the general fiber G bar, its dimension of automorphism group is indeed 2G. So it has only one difference. If the central fiber has the small has deformation group of at most 2G, then we can use the invariance of Euler character and final deformation to know that H1 of Tx0, the tangent bundle, is 0. So X0 is locally infinitesimally rigid. In other words, X0 is by holomorphic to xt for some small t, but this xt is G bar. So in this case, we know that X0 is we know the rigidity of G bar. The other case is when the dimension of automorphism group of X0 is at least 2G plus 1, because it's at most 2G plus 1, so it's equal. By the previous result, apply this previous result about this inequality formula. We know that X0 is indeed the equivalent commutative of vector group. Now let's consider we come to this case. We can we have a smooth projective family X. General fiber is G bar, is the equivalent commutative of this group G, and the special fiber, or say the center fiber, is equivalent commutative of vector space CG. Use the plus action as the group action on this variety, so it's quasi homogeneous. So the boundary is a union of prime divisors of R. The number of the irreducible component is R. So when we study this diagram, let's call it diagram, we could find that this index of this group is G, or in other words, the root lattice equals width lattice. Let me roughly explain. Here is some interesting part. Sorry, here the central fiber X0 is vector group commutative. So the Picard group is the direct sum of it's just a lattice generated by this EJ, Fourier generated. Recall that this G bar, we know we can recognize the geometric information from the theory of color bands, we know that the Picard group is wheat lattice. And the root lattice is just the subgroup generated by boundary divisors. Here, a technical thing is that after because we can and smooth information, we can identify Picard group among these fibers. Input then, and this identification, we could identify this boundary divisor Xj or J bar to be the boundary divisor Ej or this X0. So in this case, the subgroup coincides with the total group. Then we know that the root lattice equals wheat lattice. Now, note that this group G is simple. There are not so many wide group who has index 1, only 3, G2, F4, E8. So we only need to consider this these 3 cases. For these 3 cases, we reduce this diagram to smaller one. Indeed, this is a general picture. Recall that our group G has we can fix a Maxwell torus T. Consider the closure T bar, then the deformation to the central fiber. By a nice choice, we can make the central fiber to be a equivalent compactification or smaller vector space C tau. And this diagram has a group action. If we choose T to be a smaller group, we can also get a smaller family of this smaller family of Cauchy homogeneous variety, let's say. To solve these 3 cases, we choose some torus of dimension 2. We get a smooth family of surfaces. In these surfaces, we use this group action to get that this boundary divisor, not boundary divisor. The central fiber is a Cauchy homogeneous surface. Its boundary divisor has 2 subsets with its boundary divisor consists of 2 sets. These 2 sets and group action behaves weird, so this property can't be solved. This property can't be fulfilled by some surfaces. Finally, let's say we can we use a funny property about surface like this. Let Y to be a smooth projective equivalent compactification of C2, 2-dimensional vector space. Let A to be the automorphism group of Y. It's a finite subgroup. It stabilizes the boundary. Let's set to be S to be the set of irreducible components of boundary. Suppose S consists of 2 orbits and this section of A. Then the boundary divisor of Y has one irreducible at least one irreducible component is stabilized by A. Or in other words, this 2 orbits, at least one orbit has coordinate 1. It only contains 1 point, 1 element. Sorry. Okay. We can by this property we can complete these 3 cases. Finally, we know the rigidity. In the last slide, let me end up with sorry, not end up. There's still 1 case remaining. It's about the rigidity property of CR bar. Recall that in this case, we need to study a specialization problem. General fiber is the compactification of CR, and the special fiber recall that we have no the universal vulnerability. So the special fiber has the same vulnerability as general fiber. Here we can use some special property to solve this case. Recall that for type A case, we can use successive blow-up to construct the wonderful complication of AR. In CR case is similar. CR bar has a Murray contraction to some species, some variety, and the quasi-homogeneous variety. This variety is the quotient of some Lagrangian Grassmann by some involution. We can use the inverse of Murray-Cohn to extend this contraction to some relative Murray contraction over direct. Then we can use the VMRT structure on this X to study this family Z, the target. We use the associated geometry structure to study it, to find that this is Z0, the central fiber Z0 is also the quotient of this Lagrangian Grassmann by the involution. So this is a trivial family. This trivial family has a CR cross CR action, but this we can extend this action to X. So now the central fiber also has a G cross G action with open orbit G. So finally, we can find the spherical information is invariant and find that X0 is G bar. So this special case is a little different with the general case, but the stability is similar. We just use the vulnerability structure and the rigidity property of final deformation to get the rigidity. Finally, let me explain end up the talk with the construction or commodification of the CCR case. Let Y to be the Lagrangian Grassmann. This W1 and W2 are both 2R dimensional symplectic white space. This Y Lagrangian Grassmann means some special subspace of dimension 2R. Let YK to be the subset that the element U, the subspace U of this W1 plus W2, it intersects with W1 with the dimension at least K. Note that this W1, this index, lower index is not important because YK is also equals to the set of U with the intersection of W2 at least K. Let ZK to be the involution of YK by this sigma. So we have a chain, let's say ZR, Z2, Z1 until Z. Here, Z1 is prime divisor, ZR is some self-product of some flag manifold. Then this we can construct the wonderful commodification of CR by successive blow up. Firstly, blow up the smallest center CR, then blow up the street transform of ZR-1. Continue. Finally, the blow up is along the street transform of Z2. So now we get the finally we get the wonderful group commodification of this C keys. I want to end my talk here. Thank you.
Okay, thank you. So are there any questions or comments? So maybe I can ask, so in your last slide, so we see the construction of type C communication by successive blow-ups. but you start with something quotient. Yeah.
Oh.
So now I'm wondering if you start with directly y, and then you do the successive blow up along this yk. So y1, y2, and so on. And
As
then,
far as I remember, this is a double cover, nice
yeah,
double
this is double
cover
cover
of this of our construction. Yes.
Yeah, but now I think this should be a symmetrical variety. It looks like to be a symmetrical variety if you do this. And then I'm wondering.
Probably you are.
Yeah, I'm wondering.
Yes, it's symmetric.
Yeah. So I'm wondering whether this can, we can show the deformation rigidity of this.
Let me think, but it looks like to be true. Symmetric, right?
Because this y1 is just is isomorphic to this zr. Oh, this yr, so its VMRT is the same.
You mean after blow up?
Yeah.
Are you sure?
I don't know. I just
No. Usually it has some infection on the VMRT.
Yeah, I think it still be the smallest strata. I mean, to get the lines meeting the smallest strata, and you take a strict transform of this line.
Oh, you mean that?
Yeah.
Yes. It has the same VMRT with the CR bar.
Yeah, I think so. Because this is sigma fix the last stratum.
Yes, this is true. Yes, this is true.
So yeah, and so another question is for this wonderful complication. So now I'm thinking if you do further blobs, you can do further blobs. You get not minimal wonderful communication, but still somehow not minimal. Maybe also we can extend this argument to this case for some cases. So the first question is what subvariety should we blow up to stay to be final? Yeah. Usually when you blow up, then it's not final again.
Yes, but for this I need to check if only if consider final condition.
Okay.
Final. Maybe we can use the spherical information because like
use a colored fan and then you blow up.
This formula behaves well under this kind of blow up. If if we blow up some orbit or orbit closure or something, it should behave well. So, but I this is technical to me. So if to check the intersection, I can't imagine in my mind. Okay.
So are there any more questions? So you no more. Any question?
Yeah, I have a question.
Okay.
Okay.
Do you know the structure of VMRT on the boundary?
You mean the degeneration?
Yeah. At the general point of the boundary, do you know what they are?
Firstly, is that the boundary has
There's only one boundary, right? The minimal,
no, there are many boundaries.
yeah, but the minimalization curve intersect only one boundary. Right?
Yes,
In
yes.
type A case, it intersects
Two.
with the two boundary, but in other cases, it intersects with one boundary. And firstly, the certain thing is that the boundaries has different VMRT with general point. I mean, at this intersection point, but which one I'm not so sure.
I see.
So it should be no. I'm not so sure. But let's say the boundary part is a divisor. It has codimension y. So first, maybe firstly it should contain no projection of the general VMRT. No. I don't know.
Okay.
Sorry, I don't know. I'm not sure about this. What I know now is that it's different with the general VMRT.
Okay.
I even
Okay.
sorry. It should not be smooth even. Otherwise, it's rigid. So it's not smooth. Yeah.
All right. Okay. Okay. Thank you.
Thank you for the question.
Okay. If no more questions, so thank Qifeng again.
Thank you.
So yeah, so we'll have a short break, and the next talk will be chaired by Professor Deqi Zhang. So we'll restart in 30 minutes.